let's see. Can you now see the
Yes. Yeah.
presentation?
Yeah. That
Yes.
looks good. Yeah.
Okay, perfect. So thank you very much for the invitation or for the possibility for us, Anton Paar, to present our solutions today. Before we started with it, I would like to give a short introduction about Anton Paar itself, and then, of course, leave my colleague Anthony, that is our market development at Anton Paar, show you the solutions that we have for the lithium-ion battery materials, such as solid electrode materials, electrodes, slurries, separators, and current collectors, electrolytes, and also about the solutions for lead acid battery materials. So please just feel free during our short presentation to put any question that maybe appears. We are really pleasured to answer your questions. So yeah, quickly about me. I'm the general manager at Anton Paar Switzerland. I will just give you a short introduction about the company. And then, as I said before, Anthony Jaloux will show you the different solutions that Anton Paar can offer in this kind of area. Anton Paar, our here in the picture, our headquarter in Graz. We are an Austrian company with our main headquarter in Graz, Austria. Anton Paar became last year, or we could celebrate our 100 years party last year. It's a continuous explored and a determined company that has merged in high precision engineering, company in developing new instruments, new solutions, and new technologies. And this gives a little bit a picture about what kind of different instruments Anton Paar can provide. A broad portfolio from the smallest density meter that we have on the market to our really complex, high complex, sophisticated SAX measuring instruments. And if you see in the picture, we can or we are delivering a lot of different technologies and different instruments. We speak about over 170 solutions that we offer right now in our portfolio. We develop, we produce, and we sell, of course, these high precision measuring systems. And we have also an department that customizes automation and robotics with different and customer tailored solutions. About our measuring technologies that we offer in our portfolio. We go from density and concentration measurements, where we are really high known. We are also technology leader in density. We offer also instruments in the viscosimetry product area, polarimetry and refractometry. We offer this also an instrument that we have a portfolio for the different industries. We have a lot of instruments for determination of petroleum properties. We are also a market leader in the area of rheometry, and then we offer also a lot of instruments in the area of particle pore surface characterization, mechanical surface characterization, analytical and synthetic chemistry, X-rays, Raman spectroscopy, also process instrumentation to have inline measurement about the process. And in automation robotic, as I said before, we make also customer-made solutions where they are needed. We have also some special fields where we work. As I said, we are market leader in the fields of density, concentration measurement, rheometry, rheology. A lot of people knows us, and CO2 measurement. But we develop also in special fields like um, our skill lab, where we develop the system to train our talents for football. And we really invest in revolutionary training and analysis systems also for sports. Operating worldwide, Anton Paar has new production companies, most of them in the area of Germany, Austria, and Switzerland. We have 35 sales subsidiaries worldwide. If you see here in the um, yeah, map, everything that it's red market, we have local sales subsidiaries of Anton Paar. In the other areas, we work with the distribution partners. There are around 50 worldwide. How we are um, yeah, working or operating from Switzerland, we have two sites. One location in Bux, Aargau, where I'm today. So it's our headquarter in Switzerland, and we have also office and demonstration lab in Courcelles, close to Neuchâtel. Where we have also the possibility to show our instrument and solutions to the French-speaking part of Switzerland. Yeah, we have otherwise on the field 9 employees in the sales department covering complete Switzerland, and we have 8 service technicians also covering complete Switzerland to make sure that we give the best support in all the area in the complete country. And then we have 7 employees in the administration, actually, including, of course, the management, but also inside sales and marketing team. When we look a little bit to the growth of the company itself over the last years, really nice to see it's the development on employees worldwide against also the annual net sales revenues. Really important or interesting to show it's in the time of crisis where we see a decrease, of course, of turnover due to certain crises, but that we keep stable our amount of employees and resources, and we invest in the future. So we are really stable also in critical times, and this makes, of course, also Anton Paar as strong as we are doing in the last years. One of the focal points is that we put a lot of focus and resources in keeping production and assembly in-house. We try to do all the important and critical parts and critical processes inside in our company. We are not doing outsourcing. So we have really departments for mechanical production, also electronic production. A part it's done in-house. We have also the glass production, most known for our density meters that are built also inside in the company. And then we have a really large department that is doing the complete assembly and also a testing of our instruments to make sure that our systems are really stable and has the highest uptime possible. Yeah, service and support, of course, we are really focused to give the best service and support to everyone that has a solution from Anton Paar. Important for us is to keep the maximum uptime. So we offer really customized service for the different solutions on site to customers. We respect response time of 24 hours for any inquiry that comes inside. We, of course, have really advanced trainings for our service engineers to make sure that they can do and they give our customers the best support as fast as possible. And I think that this is also important to know that everywhere worldwide where you have an instrument from Anton Paar that needs support or that needs service, we are located in 86 locations, and we have more than 350 certified engineers worldwide to give to everyone this support. This slide shows a little bit a day with Anton Paar. It's more to show during a day with how many products we come in contact during our day that can be measured, respectively the quality control can be done with an Anton Paar instrument or can be characterized with an Anton Paar instrument. And this starts from the morning with a healthy start of our yogurt, also when we clean our teeth, when we go with a car to working, fuel, also at the asphalt, going through also when we have our meal, when we take our coffee, when we go home and we wash our clothes, or even in the evening if we like to drink also a glass of wine. These are all products that can be characterized or respectively the quality control with an Anton Paar instrument. So facts and figures quickly resumed. We are a company with more than 100 years history. We have our headquarters in Graz, Austria. We have more than 3,900 employees worldwide. We are owned by the Santner Foundation, and we invest, this is really an important point to know, we invest, excuse me, roughly 16% of our annual turnover in research and development. And it's why we every year also are able to bring new technologies and new solutions for our customers. All critical components are manufactured in-house, and this is a really important point for us. I hope that I could really in a short going through speed give you an basic overview of Anton Paar for whom doesn't know us yet, and open for any question if any questions are there. If no questions are open, I would otherwise give the screen to my colleague Anthony that will present you then the solutions.
All right, thank you, Ricardo. If you don't mind, please, everyone, just a reminder to please mute your microphones because there's some background noise. I believe I have about 40 minutes to present the technical part of this talk. So if you can just give me a second, I will share my screen with you. I think everyone can see my screen right now. So I'm going to go ahead and share the screen and as well turn off the camera until the question and answer, just to save some bandwidth. So now that you know a little bit more about Anton Paar, I will dive directly into the technical part of this talk. If I do exceed the time, please somebody just let me know. I know we have about 40 minutes or so, so I'll go ahead with the technical talk on this. So first, I'm going to give some basics about the lithium-ion batteries, not for educational purposes, because I know everybody on this call is already an expert in lithium-ion batteries, but just so that we're on the same page when talking about the different parts of the battery and the different parts of the tests that we do on batteries, so that there is no confusion of what part of the batteries we're talking about or what part of the testing we're talking about. So The battery production cycle goes through roughly a few hundred steps, but they can be categorized under 7 phases. So from raw material to the production of the material that are used in the battery. Afterwards, the battery components, the manufacturing of the battery components, then the manufacturing of the cell, the battery cell itself, followed by the packing of the battery cells into a module, the end use of that battery into typically a vehicle or a cell phone or a truck, etc., and then eventually to the recycling of the battery itself. So Anton Paar is somehow involved in most of these steps, from the raw materials to the battery cell manufacturing, and a little bit as well into the recycling of the batteries. Obviously, we do not produce cars and we do not pack modules, so we're not involved in this part of the industry. There are several types of lithium-based ion batteries. By far, the most researched, the most funded, the most used would be the ternary lithium-ion batteries. Ternary refers to the presence of 3 metals in the chemistry of the battery. The most commonly used metals are nickel, manganese, and cobalt. Another commercially available type of battery will be the lithium iron phosphate, or LFP. I will be talking a little bit about LFP in the next slide. And there are also some other types of lithium-ion-based batteries that are still in the research and the R&D phase, not yet ready to be commercialized, in spite of them showing very good preliminary data in terms of energy density and shelf life, etc. Regarding lithium iron phosphate, or LFP, so this is a commercially available type of battery that is currently being produced in China. It is of high interest to the battery researchers and battery manufacturers for 3 main reasons. First, because it is relatively cheap to produce compared to ternary lithium-ion batteries. 2, because of the availabilities of the material that go with it. So iron and phosphates are readily available almost anywhere in the world. And 3, because they have shown some really good safety features. So a very popular and a very mandatory type of safety test that is done on batteries is called the nail penetration test. So a nail penetration test basically is driving a nail physically through a battery cell until it produces smoke or it catches on fire. Doing so on a lithium-ion battery, a ternary lithium-ion battery, will generate fire after a certain period of time, after a certain depth of the nail penetration. BYD, which is a large battery manufacturers out of China, have done the nail penetration test on LFP batteries back in 2020 or 2021, and there was no smoke and no fire. The reason LFP has been massively produced worldwide is because there were some patents out of China that were protecting the production of such types of batteries. These patents have expired at the end of 2022. So according to all estimates, the production of LFP batteries will be increasing. It will be taking over market share compared to lithium-ion batteries as of this year. Now, the search for an ideal battery, for a researcher or a manufacturer always looking for an ideal battery, they will face what is called a battery trilemma, which is basically high energy, fast charging, and long life. You can optimize 2 of these parameters, but it's always going to be at the expense of the 3rd parameter. Now, this is not necessarily a bad thing. A typical example is a manufacturing of a battery for a cell phone, for instance. Doesn't have to be a battery that lasts 10 years, because on average, a consumer would change their phone once every year. So it's better to have a battery that is charging fast and that can last a whole day of charge. Conversely, A cylindrical cell, for example, that is used for a car needs to last for at least 10 years and also needs to have some high energy so that the driver can drive it for hundreds of kilometers without needing to charge. But that will come at the expense of fast charging. So there's always a parameter that will be suffering when developing a battery, but that is not a problem because the developers and the manufacturers always build the ultimate battery that is fit for purpose. There are several types of formats for battery cells. By far the most common ones are the cylindrical, the prismatic, the pouch, and the coin cells. The reason I mentioned this because depending on the format of the cell, the manufacturing and the quality of the material used and the quality of the coating of the electrode slurries will vary. Each manufacturer, each end product prefers a certain type of battery format. They each have their advantages and their disadvantages. So again, it's what is fit for the purpose, what is fit for the end product. Again, this is the last part of the introduction about batteries. I'm just going to, I kind of prepared this narrated representation of how a battery production is going, just so that we are on the same page and just to say in which areas does Anton Paar focus in terms of solutions for the battery production process. I hope the audio is going to work. If it doesn't, please let me know. This animation is a simplification of the process of battery cell production, which is a complex procedure that follows a process chain of a large number of consecutive individual steps. In the classic example of a lithium-ion battery, a typical cell manufacturing process starts with the production of the electrodes. For this purpose, the powder raw material of the electrode, for example, LNMC for the cathode and graphite for the anode, is mixed with a binder, typically PVDF, as well as some conductive additives. Then a small amount of solvent is added, such as NMP, which is an organic solvent. Everything is then mixed well together to form a very homogeneous slurry. The slurry mixture is then coated onto current collectors, which are typically copper foils for anodes and aluminum foils for cathodes. This coating process is followed by electrode drying. This is a very important step to eliminate dispersing liquid. It is done mainly by convection dryers with temperatures ranging from 50 to 160 degrees Celsius. Once drying is complete, the electrode is mechanically compacted by means of a calender. For this purpose, the electrodes are passed through two rollers running against each other and compacted at high line loads. This step serves to reduce the porosity of the electrode and reduces overall volume too, which leads to an increased energy density. After cutting and stacking multiple layers of electrodes and separators, everything is packed together into an enclosure and an electrolyte solution, which is a lithium-containing salt in an organic solvent, is then carefully added. And this is how a battery cell is produced. Good. So now that we have, obviously, this is a very simplified version of how a process of a battery is done, but these are the main steps where we as a company, our solutions would fit in. So I will be talking about the solutions for the physical characterization of battery materials. So a schematic representation of the battery is basically a battery, whichever types of battery will be made out of an anode and a cathode, separated by a membrane, enclosed in some sort of enclosure. There's an electrolyte solution that allows the travel of the ions, and basically this is the battery cell. We will focus on the physical characterization of the different components of this battery. So we'll start with the solid electrode material, and we'll see what kind of tests, the most common physical characterization tests done on the solid electrode material. So specific surface area, also referred to as the BET surface area, after the three scientists that have developed it, Brunauer, Emmett, and Teller, is probably the most critical physical property for battery electrode material. So this method uses gas sorption data to quantify the number of molecules of adsorbate on a monolayer of the surface of the material. in order to determine the surface area in square meters of the sample. And the measurements is done in a very specified relative pressure range from 0.05 to 0.3. This information is really critical for developers and manufacturers of battery, as it has a direct effect on the battery performance and its quality and its consistency of the end product. You can see here a typical 11-point BET plot of a typical cathode material, which is NMC, as well as a plot for a graphite material, which is a typical anode material. The final results are going to be expressed in square meters per gram of sample. And this type of data goes onto the material data sheet of the electrode material. To do these kind of plots, you need something called a surface area and pore analyzer that is available on the market. So any electrode powder manufacturer or provider, any battery cell manufacturers would most likely have a surface area and pore analyzer in their labs, whether it's in the R&D lab or in the QC lab. In a lithium-ion battery as well, the particle size and the size distribution of electrode materials affect the diffusion of lithium ions, which has a direct effect and influence on the power density and the energy density of the produced battery. So depending on the size of the particle, the technology that you use to measure them would be either based on dynamic light scattering or on laser diffraction. Typically, for cathode material, the sizes of the particles are in the micrometer range. So laser diffraction will be the most appropriate technology to measure these sizes. But for anode material and for silica-based material, we're talking about particles in the nanometer range. So DLS would be the technology of choice. There is also another important parameter to measure, and that is called the zeta potential. So basically, zeta potential is used in cases where, for example, you need to add carbon additives to your mixture to form a stable mixture. You need to have a zeta potential of these particles high enough so that the particles don't conglomerate together and form a sediment. This is important information for the developers because they would need to adjust the pH or some other parameters during production in order to have a homogeneous solution. Now, the zeta potential of particles is measured with technology called electrophoretic light scattering, or ELS. Instruments such as this one will have the possibility of doing both the size distributions, the particle size, as well as ELS, both in one instrument. Now, accurate measurements of skeletal density, it's also known as true density, by gas picnometry, will allow researchers to quickly assess new material and screen, different components of the material for the best candidate for a battery. Usually, the larger the skeletal density of an electrode material, the higher is the energy density of the battery. You use a gas picnometer. It's the technology. Picnometry is an old technology that has been used for years in order to measure the true density. Using gas, so basically what you do is you determine precisely measuring a gas volume before and after expansion into a small empty chamber. The use of gas is more advantageous compared to liquids, since the gas molecules are much smaller and can penetrate the smallest pores of the sample matrix, generating a much more precise skeletal density value. Another type of density that is very important in battery manufacturing is called the tapped density. It's also known as bulk density or packing density. This is an important parameter. So basically, it includes the volume of the solid phase plus the volume of the spaces between the particles and the volumes of the pores within the particles. For solid battery material, larger tapped density leads to more efficient energy management. For example, in cathode materials, mixed particle sizes give larger taps density and better electrochemical performance than single size or single particle size. Basically, you want in a cathode material to have a mixture of different sizes of particles so that you maximize the tap density. But again, the distribution of the sizes need to be relatively narrow. You want to have small, medium, and large size particles. You don't want to have the same size of particles because then the density, the skeletal density, is not going to be high enough, and therefore the energy density of the battery will not be high enough. The principle of measuring tap density is really very simple. So basically you weigh in a certain amount, a known amount of your material in this type of container, and after multiple taps or hundreds of taps, you basically measure the volume. And this is how the tap density is measured. Now, the overall quality and durability of a battery depends on both the type of electrode coating and also on the adhesion onto the current collector. Instrumented scratch testing can be used to measure the adhesion of electrode coatings onto the substrate. So how does this work? So basically, you would put the substrate onto under the instrument, and the scratch test will allow to gather information on the cohesion of this coated layer onto the current collector. The mechanical bonding of the particles to each other and to the metallic substrate is an important information. The type of data that you would get from this type of analysis, it's really important for the battery manufacturers. And again, it's going to depend on what kind of format the battery is. So is it cylindrical or is it prismatic, etc. So this will determine the type of coating and how the coating needs to be done. For example, here you can see that the adhesion of 3 different cathode material was assessed by an instrument that called microcombi tester. What you do here is that you increasingly apply a normal force, okay? And then you can see that sample 1 and sample 3 have suffered delamination. So they suffered damage. The coating of the slurry onto the electrode was not properly done. However, sample 2 resisted to this delamination. There are other parameters that are recorded as well during such a test, like a friction coefficient, as well as penetration depth and residual depth. This type of testing is usually done in power tools manufacturing. So, for instance, in a drill bit where the manufacturer is coating some sort of metallic powder on the drill, so that when you drill through the wall, your drill bit is not completely abused. So this is common practice for the tool manufacturers, and it's starting to be very common practice in electrode manufacturers, specifically in the Asian region. So, so far we have talked about physical characterization of the battery material, but equally important as well is the chemical characterization of many of the components of the battery. Elemental analysis by atomic spectroscopy is very important to evaluate the quality of the raw material for battery manufacturing. Why is that important? Because certain impurities at very low levels, at parts per billion levels, can not only have a bad effect on the life of the battery and on its performance, but it also can have a very detrimental effect on the safety of the battery. So it is very important to determine the purity of the material that is being analyzed. For that, instruments like atomic absorption, or AA, or ICP-OES, inductively coupled plasma optical emission spectroscopy, or mass spectrometry like ICP-MS, are typically used to assess the purity down to the ppb and even the ppq, parts per quadrillion level. All these methods have a bottleneck, and that bottleneck is proper sample preparation. So in order to do, to transform a powder material into a solution, you have to digest it, acid digest it. The most commonly used method for acid digestion is the use of a microwave. So microwave assisted acid digestion will give you a very quick, very reliable, and very repetitive type of result. For instance, you would see here the profile of the digestion that lasted about an hour. Digestion of different material will take anywhere from 5 minutes to an hour, depending if your material has silicon in it or it has graphite in it. It becomes a bit harder to digest. So you would have a digestion profile, temperature profile, as well as a pressure profile. Now, there are several different types of microwaves on the market. Depending on what is the scope of the work that you are doing, the choice will come down to, the number of samples that you have, the sample types that you are digesting, which in turn will determine the digestion temperature needed and the corresponding pressure ranges, as well as the sample quantities available for sample preparation. So for instance, if a researcher is developing material, they might not necessarily have enough of the samples, not in the kilograms like a producer, so they are dealing with milligrams. So therefore, their choice of a microwave digestion system will depend on the amount of material that they have. So microwave technology is not only useful for proper digestion of samples prior to atomic spectroscopy. Microwave technology is also useful in drastically increasing specific synthesis reaction times during cathode material development. For example, coating lithium iron phosphate, we talked about LFP, cathode material with carbon nanotubes is usually a synthetic reaction that lasts anywhere between 5 and 25 hours. And this is done in an autoclave at temperatures varying between 140 to 200 degrees centigrades. The resulting product is a highly conductive cathode material for high-powered lithium-ion batteries. This is common practice, coating carbon nanotubes on LFP to increase their energy, their power. With a microwave, though, you can accelerate this reaction down to 5 minutes. So this is a huge advantage for a synthetic chemist who's working in the lab doing this synthesis. They don't have to wait a full day, 25 hours, until they find out whether their synthesis worked or whether they needed to adjust parameters. They can find out within 5 minutes. So we've covered the solid electrode material. We're going to now look at the slurries. As a reminder, slurries is basically the solid electrode material that is mixed with some binders as well as some solvents. The rheological properties during the manufacturing process of a battery component are very important. Again, there is no battery production site that would not assess the rheological properties of their slurries throughout the stages of their production. There are 4 areas in the production process where the rheology is very important. The rheology of the powders themselves, the sedimentation stabilities of the slurry. So when the slurry is mixed together, how does it sediment? Is it stable or not? The behavior of the slurry when you are mixing it, and then the flow behavior of the slurry when you're pumping it or when you're coating it. And we're going to be talking about each one of these properties and each one of these rheological areas separately. So first, with the rheology of powders, parameters such as compressibility, cohesion, and internal friction angle at different humidity levels are important to characterize. So for that, accessories such as a powder shear cell or a powder flow cell are used depending on the flow and how dense is the material that is being investigated. In this example, we can see that the addition of silica powder to carbon material used in batteries makes this material denser. Silica powder is sometimes added to anode material to increase its energy density. And because of its brittle behavior, silica powder also increases the flowability of the whole powder mix. and is therefore acting as what is called a flow aid. You can also see when you do the rheology of the powder, you can see sometimes important information such as this one. For example, silica powder, based on what we see here, it densifies very easily and under its own weight. So the extra normal stress that we are putting on it doesn't affect much its solid density. And this is what the blue plot here indicates. We're going to talk now about the sedimentation stability of battery slurries and why is that important. So for that, you use a rotational rheometer. Okay, these are perfectly ideally suited to measure rheological properties because they can simulate the process relevant conditions that would determine the physical elastic properties of that slurry. So basically, one of the classic tests performed with a rheometer is, and other Newtonian fluids, is called the frequency sweep. So the frequency sweep generally provides information about time-dependent behavior during a test. So what you do during the test is that you increase the frequency of the rotation, but you keep the strain at a constant rate, and you keep the temperature at a constant rate. In this example, the sedimentation stability of two slurries was evaluated. We can see that slurry B shows better sedimentation stability at a low angular frequency. So this means that this slurry here is going to be much more stable. It's not going to show phase separation as compared to this slurry here, slurry A. This is assessed by the crossover point of the G prime and the G double prime, which are the storage modulus and the loss modulus. Again, these are rheological properties of any material. The software will give you the crossover point of the storage modulus and the loss modulus. You see the angular frequency, and then you decide how stable is your slurry. A relatable example of applicability of this is the cement trucks that you would see driving to a construction site. They have a cement mixture in there. And you see that the whole vessel is turning, is rotating continuously. Why? It's because the scientist in the lab did a test like this and told the driver, you need to keep turning this drum at an X rounds per minute so that the cement in the truck doesn't solidify. And this type of test is what is called the frequency sweep with a rheometer. So now that we know how the slurry behaves when it's sedimenting, we need to see how the slurry behaves when it's being mixed. For that, you use a rheometer again to determine the yield point and the structural recovery, which is also known as thixotropy, to see if this is a shear thinning or shear thickening slurry. Both the composition of the slurry as well as the mixing route chosen will determine how it's going to behave. The graph here is a typical representation of how the increased amount of material or solid fraction in a slurry increases its viscosity, and how the highly concentrated slurry starts displaying non-Newtonian behavior, which means they show some shear rate dependent behavior. What does it mean? It means that the more material you add to your slurry, the less it's going to start behaving as a Newtonian fluid. What's a Newtonian fluid? A Newtonian fluid, for those who are not familiar with rheological terms, typical Newtonian fluid is water and some oils. So basically, if you add sugar or salt to the water, it's no matter how much you start adding sugar or salt to that water, the viscosity is going to start increasing, but it's going to increase at a steady rate. In a slurry, the viscosity is going to increase, but then it's going to start showing non-Newtonian behavior. So it's going to start thickening or start behaving as thinning. The more you add, the more you stir. And finally, in terms of rheological properties that are important, let's look at the effects of the rheological properties when pumping or coating a slurry. To study this, a classical rheological test is called amplitude sweeps. Okay, these tests are useful in practice to describe the behavior of the slurries, which in turn determines the behavior during a process. So The amplitude sweeps here, you keep the frequency stable. So if you see the distance between the two peaks is constant, but what you change here would be the strain. So the amount of shear strain that you are putting on the material. The results of such tests are exemplified in this graph here. So in this example, for instance, you can see that the crossover point of the two constants that we talked about, G prime and G double prime, are plotted for different slurries. And you can see for this slurry, which is slurry 3B, it has a crossover point that is approximately 22 times higher than this slurry. This translates into real life that it takes 22 times more effort to make this slurry pump as compared to this one. And this type of information is important for someone like the process engineer who's building a plant to know how much effort, how much power they need to give their coating apparatus in order to quote that slurry onto the current collector. All this is done again by a viscometer. Sorry, by a rheometer. Now, for slurries that are not really very thick or viscous, a fast and accurate quality control check at a production site would be the single point viscosity determination. This parameter will give a production site a valuable and quick QC checkpoint in order to adjust the production parameters where or if needed. So if you need a quick check and your slurry is not really viscous, you can do a quick 1-point check of your viscosity. You keep the temperature and the speed constant and you get the viscosity. And if the slurry is temperature or shear rate dependent, then you do a multi-point measurement such as shown in this graph. Some of the data that will be given would be the flow index. So the flow index is a description of the Newtonian or the non-Newtonian behavior of a sample. If a flow index is smaller than 1, that indicates that the slurry is shear thinning, like in this case. So the flow index of water, for instance, is 1. Anything that is below 1, that means the more you stir the slurry, the thinner it's going to become. And a flow index that is higher than 1, it's shear thickening. That means the more you stir it, the thicker it's going to become. So we have previously seen that gas picnometry is an excellent tool for determining the skeletal density of the powder electrode material, but it also can be used to determine the density and the percent of solid fraction in a slurry as well. So this table shows excellent correlation between the percent of solids formulated and the percent of solid calculated. Again, it's based on gas picnometry data. This information is quite useful when optimizing the surface area of the solid electrode on a volumetric basis. So we'll now have a look at some of the common physical characterization tests performed on porous separator membranes, which are typically some sort of a polymer such as polyethylene or polypropylene. So for separator membranes, the pore size and the pore volume are important parameters to quantify. The techniques used in this case are capillary flow porometry for pore size and mercury porosimetry for pore volume. The pores that are characterized in separator membranes are called through pores, and that is because they allow the exchange of ions during charging and discharging processes. So in a porometer such as this one, a cut sample of the separator membrane will be loaded onto the sample holder here. A wetting agent is added, and once sealed, the pressure is applied gradually to measure the flow of that wetting agent through the membrane. In the graph here on top, you can see that there is no flow of liquid until a pressure of approximately 11.5 bars is reached. So this corresponds to the largest pores of the membrane that allow the liquid. So at the largest pore of the membrane, when a pressure is reached approximately 11.5 bars, this is where the liquid starts flowing and then emptying with the smallest pores of that membrane. The graph here on the bottom shows the measured data converted into cumulative pore flow percent and differential flow percent values versus the through pores. So the red peak at approximately 0.055 microns or 55 nanometers corresponds to the mean value of all the pores in that membrane. So that was done by pyrometry. Now that
Anthony, can I? It's you have about 3-4 minutes more, and then we would like to go to the question. Is that okay for you?
Okay, I will zoom through it then. Yes, thanks for letting me know. Okay, so this is basically, I'm almost halfway through, but I'll try to condense it as much as possible. Mercury porosimetry is another test done on the membranes, and if the data from the mercury porosimetry and the pyrometry are very close, that means the membrane has all through pore sizes, which is the actual desired result for a porous membrane. Other types of tests done on the membrane and on current collectors is dynamic tests on how much it tears, how much it supports the pressure from the manufacturing. And this is done with a fixture that is hooked up to the rheometers, because the rheometers have very, very sensitive engines. So with the proper sample modules, you can do dynamic mechanical analysis of the different parts of the battery cell. Quickly talking about the electrolyte solutions, some of the main characteristics of the electrolyte solutions, physical characterization would be the viscosity of the electrolyte solution, determined with a viscometer, will be the density of the electrolyte solution with a density meter, and also will be there is chemical tests done like we saw, purity of the electrolyte solutions. Finally, structural properties. This is where we come into a bit of an advanced science. Basically, small angle X-ray is a type of measurement where you study the nanoscale composition and how it behaves under different conditions. You use a SAX system. The SAX system usually is, you will find it in large laboratories funded by government. In at least once, one laboratory per country would have a SAX system to study not only battery material, but different kinds of material as well. XRD system or XRD system is X-ray diffractometer. This is a very useful tool for battery manufacturers. Every battery manufacturer will have an XRD in their lab. The two important characteristics that you can get with an X-ray, with an XRD, would be the crystallinity, degree of crystallinity of the material. So the more crystalline, the better. And the impurity, when you compare the diffractograms of a known pure compound versus one that is unknown. You can also do in situ or in operando, so under non-ambient atmosphere, you can check the behavior of the battery component, all its components, how it behaves under different conditions that mimic real life, such as high temperature. And for that, you have specific cell holders that will be able to do this for things like pouch cells, coin cells, etc. Sorry, I had to rush through this, but this is kind of a summary of most of the technologies, most of the solutions that Anton Paar has for the battery material. I don't know if we have time for questions. If we do, I'll be happy to answer them. If not, here's my email address. Please feel free to send me an email with any questions you might have. Thank you very much.
Yeah, Anthony, thanks a lot for your introduction. Sure, we take the time to answer one or two questions. That's not a problem. I know there are many different machineries that you have, and especially for the electrochemists here in the audience, I think this is very interesting, and the material specialist. So questions to Anthony. Everybody seems to be very quiet
I
here.
would have a question.
Great.
This is Petra Christoffel from Polymer Competence Center in Leoben. I like to ask you, how would you characterize the elastic modulus of the anode, cathode, or also of the separator?
So the elastic modulus, there are specific holders that are that can be mounted on the rheometers. There's a specific rheometer that will have two drives, a drive that is situated on the top and one that is situated on the bottom. These drives have very sensitive mechanics. They are air bearing. We can equate the sensitivity of this to the amount of torque that a single hair has on an extended arm. So with that, you have specific holders, cantilevers, etc., that can be mounted onto these rheometers and be able to determine the elastic modulus of such material.
Okay, thanks. I think we have such a rheometer.
Okay, that's good.
I have then another question from Tu. His microphone is not working, so he was asking, how would you evaluate the dryness of an electrode?
How to evaluate the dryness? That's more of a process question. I will answer it not based on my direct experience, but based on my research. So typically when you coat the slurry onto a current collector, this goes to, you allow it a certain time depending on the rheological property of the slurry that we have seen based on the sedimentation stability and based on the pumping and the homogeneity of the slurry. So you allow it a certain time to dry by itself. Then this goes through ovens at around 150 degrees and they dry. However, there's also a possibility to use drying with the use of UV. So there's UV drying that is also available on the market. And then once you're done with this process of drying, this is studied basically on a smaller scale first. It goes through calendering. So the calendering is basically compressing this at very high, relatively high pressure. So you compress this, it's rolling through the calender to eliminate any residual solvent that might have not evaporated during the heating, during the drying. With these two processes, you're pretty sure if there's something trapped still in the slurry or in the coating, then that's an indicator that there might be something wrong with the formulation of the slurry. But that again is based on my theoretical research, not on direct experiment.
Good. Is there another question from the audience? If not, maybe I would ask a question. So now we talk mostly about the production of batteries, but now as especially Europe tends to go to a circular economy,
Yes.
do you work also specifically with secondary materials, or you have what are you working on in that field on the characterization of materials?
Well, that's a great question. And the answer is, so as far as our company is concerned, we do work with recycled material. We do the testing of recycled material. Primarily for now, if you recall on one of the slides, I showed recycling in a dotted circle. The reason for this is that we haven't fully developed the entire portfolio of testing on the recycled material. One of the main applications for recycled material is the characterization of black mass. So black mass is basically taking a full battery or full battery pack, incinerating it, condensing it into one big lump of black mass. This can be further qualified and further quantified. But the first step to do this is to do the digestion of this and see what is it made of, so to know how to extract it. So the digestion of the black mass is a relatively tricky process. And this is done usually with microwave technology. So you take a portion of this black mass, you put it in a tube, you add specific acids or acid mixture, and you run a digestion process. So this is only one of many, many different parameters that you can assess. There are upcoming studies and application notes, as well as research papers that we're going to be publishing later on this year concerning the recycling of battery material. So this is, I can't divulge much, but this is as far as I can say that, yes, we are working on recycled battery material as well.
Yeah, great. I think